Welcome to another video from my series about probability theory. In this one, we will finally arrive at a non-naive definition of probability, which will be used most of the time from now on. In contrast to the naive probability we have seen so far, it is less restrictive and more suited for real-world application. Let us briefly recap what we mean when we talk about naive probabilities, and analyze what we will gain when moving on from the naive definition to the non-naive one. In the naive case, we looked at sample spaces which were divided into an equal grid. Now, let's also consider sample spaces which are irregularly spaced and have any possible form. So, we are moving on from events that have an equally sized mass which led to an equal probability, to random events that consist of irregular partitions and have non-equal probabilities. We have also seen that in the naive case, we had to compute probabilities by counting the possible number of outcomes of a random experiment. This implies that we can only have countably many events. With the non-naive definition of probability, we can also have infinitely many, as long as we satisfy some conditions. We will now take a closer look at exactly these conditions. With the new definition of probability, we always need to consider a probability space, which consists of two things. First of all, a sample space, which describes all possible outcomes of the experiment we are looking at. An event of the random experiment is then a subset of the whole sample space. The second thing that we need is the probability function p, which maps a subset of our space or an event to a real value between 0 and 1. In the naive case, this function was the fraction between the size of our set divided by the number of outcomes in the whole sample space. Now, this function can be defined however you want, but it needs to give only values between 0 and 1. Additionally, our probability space needs to fulfill some more conditions, such that we can work with it. There are two main conditions that need to be considered. The first one gives us properties of our probability function. The probability function evaluated with the empty set should result in 0, while the probability function of the whole sample space is 1. You can interpret this as follows. The outcome for any event in the whole sample space of course is 1, since it would not be possible that an experiment will not give you any result. On the other hand, the probability of the empty set is 0, which basically means the same. The second condition of probability spaces tells us how we can deal with multiple experiments or events. If we have n events which are all mutually exclusive, which means that the outcomes in the sample spaces do not overlap, then we can compute the probability of the union, so the combination of the three events, by the sum of the individual probabilities. This principle can be illustrated in the following way. Assume that you have this sample space with three events A1, A2, and A3. The probability of the union of the three events is the probability of the first one, plus the probability of the second one, and the third one. Before we continue our journey, I want to give you a quick overview on how to interpret probabilities. There are two main ways of thinking about the value of the probability function: the frequentist approach and the Bayesian view. In the frequentist approach, one sees this value between 0 and 1 as the average of a very large number of experiments. For example, if you flip 10 to the power of 6 coins, then half of the coins will land on tails and the other half on heads. This gives you a probability value for the function p of 0.5 for heads and 0.5 for tails. In the Bayesian view of thinking, the probability gives you a degree of belief, so how sure or unsure you are about something. For example, you might be uncertain about the result of an election and say that candidate A will win with a probability of 0.8, even though they might not do it 10,000 times. In any case, be it Bayesian or Frequentist, the conditions for probability spaces always need to be fulfilled. Now, we will gain some deeper insights on how they can be utilized to obtain a more in-depth understanding of the properties of probability spaces. Remember our two rules. The probability of the empty set is 0, and the probability of the sample space is 1. Also, the probability of disjoint sets can be computed from the sum. We will now prove a property that we have already seen in the naive case. The probability of the complement of a set can be computed from 1 minus the probability of its complement. Assume we have this sample space with the event A. Then the complement of A is everything not covered by A. We will use the fact that the whole sample space is given by the union of A and its complement, and also that A and its complement are disjoint. We invoke the first rule, which gives us the probability 1 for the whole sample space. Then, we use rule 2 to compute the probability of the union from the two separate ones. We just need to rearrange for the probability of the complement of A and get our result. This can of course also be done for the probability of A. The second property that we are going to prove is that if A is a subset of B, then the probability of A is smaller or equal than the probability of B. This can be illustrated by the following sample space with the sets A and B, where A is within B, so a subset of B. We can rewrite B as the union of A and the intersection of B and the complement of A. Let's visualize this. Here we get the outer ring of B without the set A. Then A and this outer ring are again disjoint, and we can compute the probability of B using the sum of the individual probabilities, using our second rule. We defined the probability function as a function which gives us values between 0 and 1, so this term can never become negative. Thus, the probability of B will always be larger than the probability of A, since here we can only add something positive. It is possible that the two are equal, but only if this outer ring I drew is empty and thus A is equal to B. This is also a very nice result, since it shows that we have to get the same probability for two sets which are the same. The last property we are going to show is one that can be very intuitively explained, but it is a bit trickier to prove mathematically. Maybe try if you can find the solution yourself before you continue. The property is the following. The probability of the union of A and B is the same as the sum of the probability of A and B minus the probability of the intersection. It is easier to understand when we take a look at the diagram of this property. We have A, B, and the intersection of the two. What we are interested in is the probability of the two sets together. We cannot simply add the probabilities up, since the two sets are not disjoint. So we subtract the part in the middle, such that we do not count it twice. Sadly, this does not count as a proof, but we will come to that in a second. First of all, we analyze this union, which can be rewritten as the union of A and the intersection between the complement of A and B, similar to the previous proof. Now, the two sets are disjoint, and we can utilize the second rule. We obtain the left-hand side for the equation that we want to prove, and part of the right-hand side. What is left to do now is that the rest of the right-hand side of the equation that we want to prove is equal to the other part of the equation that we obtained. we write down B in an alternative way, so it becomes the union of two disjoint sets. First of all, we have the intersection between A and B, which we are interested in, and then also the intersection between the complement of A and B. Due to the two sets being disjoint, we can write down the probability as the sum of the two probabilities again. Now, we obtained a term for the probability of B, which we can insert into our proposition and see what happens. This term here cancels out, and what is left is the right-hand side of the equation that we wanted to reformulate, such that it becomes equal to our proposition. It is important that you know how to handle these set reformulations and operations, so if the explanation was a bit too fast, do not hesitate to go back and write down the steps for yourself slowly. Now that we really understand what probability really is, how it is defined, and how we can use sets to manipulate it, we can move on to actual probability theory problems. I hope that you learned something new from this video, and that you will continue on this journey of learning probability theory. For this, you can check out my playlist, where I derive fundamental concepts and also show how they can be applied in practice.